There is a machine that costs more than a commercial airliner. It fires a laser 50,000 times per second at droplets of molten metal smaller than a grain of dust. And for over a decade, exactly one company on planet Earth knew how to build it. One company, one country. Every advanced chip in your phone, your car, your military systems, all of them passed through this single bottleneck. And the entire geopolitical order was built around the assumption that this bottleneck would never ever be broken. And then Shanghai said otherwise. Think about that for a second. The most complex manufacturing system ever conceived by humanity, a machine with over 100,000 components, mirrors so precise that if you scaled them to the size of Germany, the biggest imperfection would be smaller than a millimeter. And China just built one. Not bought one, not smuggled one, designed and assembled one, using a method that the incumbent never even bothered to patent because they thought it was too crude to matter. This is happening right now, today, and the markets already felt it. The moment the news broke, shares dropped. Not Chinese shares, Western ones. If you're new here and you want to understand how the world is being rebuilt from the inside out, hit subscribe. It genuinely helps this channel, and trust me, the next few years are going to produce story after story like this one. Let's get into it. To understand why this matters, you need to understand what a lithography machine actually does. And I promise you, once you see it, you will never look at your phone the same way again. Every chip on Earth starts as a blank silicon wafer, smooth, featureless, like a mirror. And then a lithography machine draws the circuit onto it. Except draws is not the right word. It projects it. It uses light, ultraviolet light, to etch transistor patterns onto silicon at a scale so small that the features being printed are measured in single-digit nanometers. We are talking about structures that are 500 times smaller than the width of a human hair. Now here's the thing, the smaller you want those transistors, the shorter the wavelength of light you need. And for years, the industry used what's called deep ultraviolet, DUV. Think of it as a very fine-tipped pen. It worked. It built the chips that powered the smartphone revolution, the internet era, everything up until about 5 years ago. But then the industry hit a wall. The transistors got so small that DUV light literally could not resolve them anymore. The pen tip was too thick, the lines blurred. You physically could not shrink further without the image smearing. Enter extreme ultraviolet, EUV. Light with a wavelength so short, 13.5 nanometers, that it can print features 3, 4, 5 times smaller than DUV ever could. That is not a metaphor. That is just the physics. But here's the catch that kept the entire world dependent on one company for over a decade. EUV light does not behave like normal light. It gets absorbed by everything. Air absorbs it, glass absorbs it, every lens material absorbs it. You cannot build a normal lens system for EUV. You need mirrors instead of lenses. Mirrors so perfectly shaped that any deviation would destroy the image. And you need a vacuum. The entire machine operates in vacuum. No air. No contamination, nothing, and the source of that EUV light. That is where it gets truly insane. You take tin, ordinary tin, and you blast it with a laser. Not once, not twice, 50,000 times per second. Each blast turns a microscopic droplet of tin into plasma, hot enough to emit EUV photons. 50,000 tiny explosions, every second, inside a vacuum chamber, without ever touching the walls, for hours. For days, for months of continuous operation. That is what ASML built. And for more than 10 years, nobody else could. Not Intel, not Samsung, not TSMC, not any government program anywhere. One company, Veldhoven, Netherlands. Population under 100,000. And they held the keys to the entire advanced semiconductor industry in their hands. And the world was fine with that arrangement. Right up until it wasn't. Now, here's the question you should be asking. If this machine is so important, and it is arguably the single most important piece of industrial equipment on Earth, why did nobody else build one? Why did China, with all its resources, all its ambition, all its manufacturing might, not just replicate it? The answer is not that they didn't try, they did, for years, and they failed. And the reason they failed reveals something crucial about how technological monopolies actually work. Because here's the thing about ASML's EUV machine. It is not one invention. It is a stack of thousands of inventions, layered over 30 years of development. The light source alone required breakthroughs in laser physics, plasma dynamics, debris mitigation, collector mirror coatings. The projection optics required Zeiss, yes, the camera lens company, to develop mirrors so flat that across their entire surface, the tallest deviation is less than 1 atom's diameter. The alignment systems, the wafer stages that move with nanometer precision at acceleration forces that would rattle a human skeleton apart. Every single subsystem was its own decade-long R&D program, and ASML did not do this alone. They had a supply chain of over 5,000 specialized companies. Mirrors from Germany, lasers from the United States, chemicals from Japan, software from Israel. It was not a Dutch machine. It was a Western machine, a coalition machine. And the export controls made sure that no single component ever crossed certain borders. So when China tried to build its own EUV system, they were not facing one competitor. They were facing an entire ecosystem, a supply chain deliberately designed to be impossible to replicate outside the coalition. And the sanctions made it explicit. No EUV machine would ever be sold to China. No components, no blueprints, no personnel. The assumption, and this was stated openly in policy papers and think tank reports, was that China was 20 years away, maybe 25, that the complexity was simply too vast, that you cannot shortcut 30 years of accumulated know-how with money alone. And for a while, that assumption looked correct. China's lithography program struggled. They could build DUV machines, the older, coarser technology, but EUV seemed like a different universe, a different physics problem, a different civilization's achievement. The West got comfortable, and comfort, as it turns out, is the most expensive emotion in geopolitics. So here's the twist. And this is the part that changes everything. China did not build a copy of ASML's machine. They did not try to replicate the tin-droplet laser system. They did not try to match Zeiss mirror for Zeiss mirror, component for component, 30-year R&D program for 30-year R&D program. They went sideways, and the method they chose is called Laser-induced Discharge Plasma, LDP. And if you have never heard of it, that is by design, because for years the established lithography world considered it a dead end, a curiosity, a laboratory trick that could never scale to the precision required for chip manufacturing. Here's why. ASML's approach, the tin-droplet method, works by hitting a falling droplet of molten tin with a CO2 laser. The droplet vaporizes into plasma. The plasma emits EUV light, but it requires extraordinary precision. The droplet must be exactly the right size. The laser must hit it at exactly the right moment. The whole thing happens 50,000 times per second. It is a ballet of controlled explosions, beautiful, precise, and protected by a wall of patents so thick that navigating around it would take another decade. LDP takes a completely different path. Instead of hitting a falling droplet, you create a discharge between two electrodes, a spark. Like a lightning bolt, but controlled, confined. That discharge vaporizes a small amount of tin, or in some configurations lithium, into plasma. And that plasma emits EUV light. Same physics at the end, different path to get there. Now, the reason the incumbents dismissed this is that early LDP sources were dirty. They produced debris. Electrode erosion contaminated the optics. The light output was lower. The pulse repetition rate was harder to control. For the precision demands of leading-edge chip manufacturing, it looked insufficient. Too messy, too unstable. A poor man's EUV source. But here's the brilliant part, and I want you to really hear this. China did not need to make LDP as clean as ASML's tin-droplet system. They needed to make it clean enough, and then they needed to solve the debris problem differently. And then they needed to pair it with their own optics, their own alignment systems, their own vacuum engineering, built from scratch, without the baggage of 5,000 suppliers who answer to export control regimes. Step 1. Generate the plasma using a discharge rather than a laser-on-droplet system. This eliminates the most patented, most export-controlled subsystem in the entire ASML stack. Step 2. Manage the debris. Instead of relying on hydrogen buffer gas the way ASML does, which requires its own complex delivery system, Chinese engineers developed a combination of magnetic field confinement and pulsed gas jets to keep tin particles away from the collector mirrors. Step 3. Build the projection optics domestically. This is the hardest part. Mirrors that reflect EUV light with less than a fraction of a percent loss across multiple bounces. China invested in developing molybdenum silicon multi-layer coatings at State Optics Labs. Not perfect, not yet matching Zeiss, but functional. Step 4. Integrate. Put the light source, the optics, the wafer stage, the vacuum system, the alignment sensors, all of it, into one machine, and make it work. Not in a lab demo, not for one exposure, for sustained operation. And they did it. A Shanghai-based firm. The reports say prototype. The reports say it works, and the markets believed it. Because when the news hit, it was not Chinese semiconductor stocks that fell. It was ASML. It was the Western supply chain. The assumption was dead, and dead assumptions do not recover. Now, I know what you're thinking. A prototype is one thing. Mass production is another, and you're right to be skeptical. So let's look at what else is happening simultaneously, because this is where the story shifts from interesting lab result to industrial reality. While the EUV prototype made headlines, something quieter but arguably more consequential was already underway. China began low-volume production of domestically built immersion DUV lithography machines. Not EUV, DUV, the generation before, the workhorse technology that still produces the vast majority of chips on Earth. Chips for cars, chips for appliances, chips for industrial controllers, chips that do not need 3-nanometer precision but absolutely need to be manufactured somewhere. And here's the number that matters. Around 5 domestically built DUV systems are planned for delivery this year. 5 sounds small. But remember, 5 years ago, the number was 0. China had no domestic lithography capability at the immersion DUV level. None. Every machine came from ASML or Nikon or Canon. And now there are 5. And next year there will be more. And the year after that, more still. This is not a sprint. This is an industrial ramp. And industrial ramps, once they start, have a momentum that is almost impossible to stop. And the investment behind it is staggering. China's semiconductor self-sufficiency drive is not a single program. It is a national architecture. The Big Fund, China's state semiconductor investment vehicle, has deployed tens of billions of dollars across the supply chain. Not just lithography, photoresists, etching tools, deposition systems, metrology. Every single link in the chain is being rebuilt domestically, simultaneously. And the policy layer is just as aggressive. Export controls on Chinese-made drone technology to the United States. Countermeasures against American firms. A tightening of domestic IP protection around chip manufacturing processes. The message is clear. You locked us out of your ecosystem. We are building our own. And we are not waiting for permission. Meanwhile, the talent pipeline is enormous. Thousands of lithography engineers trained in the last decade. State labs in Shanghai, Beijing, Changchun dedicated to optics and light source physics. University programs producing specialists who 10 years ago would have emigrated to work at ASML or Intel. Now they stay. Now they build. And here's the strategic logic that makes this terrifying for the incumbent. China does not need its EUV machine to match ASML's latest generation on day one. It needs it to be good enough. Good enough to produce 7-nanometer chips. Good enough to serve domestic demand. Good enough to remove the kill switch. Because right now, the entire Chinese tech industry operates under a sword. The sword of access revocation. If the West decides tomorrow that no more chips, no more machines, no more software updates flow eastward, the lights go out. The EUV prototype removes that sword. Even if it is slower, even if the yield is lower, the dependency is broken. And that changes every calculation downstream. The market reaction confirmed it, not because the prototype changes next quarter's earnings, but because it changes the 10-year trajectory and markets' price trajectories. But here's the honest part of this story. And I want to be straight with you, because this channel does not do hype. A working prototype is not a production tool, and a production tool is not an ecosystem. The ASML machine that it replaces did not arrive as a finished product. It arrived after decades of iteration alongside its customers. TSMC and Samsung and Intel co-developed processes with ASML. They tuned the machine to their fabs. They built entire manufacturing recipes around its specific light profile, its specific alignment tolerances, its specific thermal behavior. That co-development is not something you can shortcut. It is years of back and forth between the tool maker and the chip maker. China's EUV prototype exists, but the yield, the percentage of chips that come off the line functional, is almost certainly well below what TSMC achieves with ASML tools at the 3-nanometer node. The optics are functional, but they are not yet at the atomic level flatness that Zeiss delivers. The light source is stable enough to demonstrate, but whether it runs for 1,000 hours without degradation is a different question. And the DUV machines, the 5 planned for this year, those are generationally behind. They are producing chips that ASML's DUV tools produced 5, 6, 7 years ago. That matters. It means China's domestic lithography, for now, serves the middle of the market, not the cutting edge. So no, this is not the moment where China leapfrogs the entire Western semiconductor stack overnight. That is not what happened. But here's what did happen. The ceiling was removed. The assumption of permanent dependency is dead. And every year from here, the gap narrows. The optics improve. The yield climbs. The next prototype addresses this year's limitations, and the one after that addresses the next set. That is how industrial capability compounds. Not in a single leap, in 1,000 small steps, each one building on the last, each one impossible to sanction because it was built at home. None of this erases the decade-long head start ASML still holds. It simply marks the distance between impossible and inevitable. And that distance, it turns out, was shorter than anyone comfortable with the status quo wanted to believe. Which brings us back to the bigger picture this whole story has been building toward. Because this is not really about lithography. It is about what happens when a monopoly meets a motivated challenger with infinite patience and a domestic market of 1.5 billion people. For 30 years, the global chip industry was architected around a single point of failure. One company, one coalition, one choke point. And that architecture was not an accident. It was a choice, a strategic decision that efficiency and specialization were more important than resilience. That it was fine for the entire world's computing future to flow through a town of 100,000 people in the Netherlands, because the geopolitical order would never fracture enough to make that a problem. And then the order fractured. And now we are watching the rewiring happen in real time. Not in a decade, not in a generation. Now, this year, this quarter, 5 DUV machines shipped, 1 EUV prototype demonstrated, a national strategy executing on every axis simultaneously: talent, capital, policy, IP protection, export countermeasures. The world that ran on a single choke point didn't announce its own ending. It just started losing ground to something that was never supposed to exist, a machine built by people who were told it could not be built, using a method the incumbents dismissed as too crude to matter. In a country that was given 25 years before it could catch up. It did not take 25 years. And here's the question I want to leave you with. The one I think about every time a story like this breaks. We are watching the global technology order split into 2 parallel systems, 2 stacks, 2 supply chains, 2 ecosystems that do not talk to each other, do not depend on each other, do not need each other's permission. And once that split is complete, truly complete, not theoretically but industrially, it does not reverse. You cannot unbuild a supply chain. You cannot untrain an engineer. You cannot unprove that something is possible. So the question is not whether this changes the world. It already has. The question is, which half of the split do you think will iterate faster, now that neither one needs the other? Because the answer to that question shapes the next 50 years of human civilization. Drop your answer in the comments. I read every single one. And if this kind of deep dive is your thing, if you want to understand not just what is happening, but why it matters and how it actually works, subscribe. We are building something here, and the next few years are going to be the most interesting decade in industrial history. You are going to want a front row seat. I'll see you in the next one.